Fire and ice, the chemical reaction that happens in cold. Some chemicals are capable of burning in the coldest of environments, a phenomenon that defies common understanding. One such chemical is potassium. Under typical conditions, fire needs heat and oxygen, but potassium is a special case. When potassium is exposed to water, it reacts violently, producing heat and a gas known as hydrogen. This reaction is so intense that the hydrogen ignites almost instantly, causing a fiery explosion. The heat released from the potassium-water reaction is enough to ignite the hydrogen, even in frigid temperatures. Normally, we think of fire as a product of heat, but potassium defies this idea. The hydrogen gas is so flammable that it creates a visual spectacle. This unusual reaction happens because of the immense energy released by the potassium as it reacts with water, which breaks the bonds of hydrogen atoms and releases them as gas. What's even more surprising is that potassium reacts similarly with other compounds, including alcohols and oils. The reaction with oils can cause a fire to continue even after the source of heat is removed. This gives potassium a truly unique ability to burn, even when you would expect the opposite, providing an extraordinary visual and a truly fascinating example of chemical behavior. So, despite being in cold environments, potassium can start fires in ways that most would consider impossible. Understanding these reactions can open a window into how energy can be harnessed and how even the simplest elements have surprising properties. This chemical is also used in different industries, like the production of fertilizers and other essential compounds. Its volatile nature makes it highly dangerous, but also incredibly useful in the right settings. However, its ability to produce heat and fire in freezing environments stands as one of chemistry's most surprising and unusual traits. Many high school chemistry classes demonstrate this phenomenon as an experiment, and it's one of the most memorable chemical demonstrations. It's not just a fun experiment. It also shows how energy can be transferred, released, and converted in unexpected ways. The fire and ice reaction is a demonstration of how chemistry challenges our expectations and leads to new discoveries. In some cases, potassium's reaction to water can lead to further dangerous consequences. The release of hydrogen gas increases the explosive potential, and in confined spaces, the result can be catastrophic. This emphasizes the need for proper safety precautions when working with reactive elements. Lastly, potassium's behavior illustrates how chemical reactions are more complex than they seem at first glance. Even simple interactions between elements can lead to extraordinary outcomes that may leave people in awe and with more questions than answers. The Belousov-Zhabotinsky reaction, the dancing colors. In the world of chemistry, some reactions take on a mesmerizing life of their own. One such reaction is the Belousov-Zhabotinsky (BZ) reaction, a type of oscillating reaction that seems to defy the traditional expectations of chemical reactions. This reaction is known for producing beautiful and rhythmic color changes, often shifting between blue, red, and clear in a repeating cycle. What makes this reaction so special is its ability to oscillate or change repeatedly over time without the addition of any external stimulus. The reaction involves the oxidation of malonic acid and its derivatives, which interact with bromine and a metal catalyst, typically cerium or silver. What results is a mixture of chemicals that goes through cycles of color change, like the ebb and flow of a tide. The most striking feature of the BZ reaction is how it seems to dance. As the reaction progresses, the solution shifts from one color to another. It starts as a clear liquid, then turns blue, then red, and back to clear, repeating this process in a dynamic rhythm. The color changes are linked to changes in the concentration of the reactants and products. When one chemical is consumed, another builds up, triggering the oscillation and resulting in the vivid shifts of color. Scientists were initially baffled by the phenomenon when it was first discovered in the 1950s. The BZ reaction defies the typical patterns seen in chemistry, where reactions generally move toward equilibrium, a steady state where the concentration of products and reactants remains constant. The oscillating nature of the BZ reaction, however, suggests that chemical systems can behave in complex and unpredictable ways that were previously unknown. The BZ reaction is an example of non-equilibrium thermodynamics, a branch of chemistry that explores how systems that are far from equilibrium can exhibit complex behaviors. It is a prime example of how nature can exhibit unpredictability and beauty in seemingly random processes. The oscillating reaction has since been used in scientific studies to explore more about how reactions can maintain their rhythm and how chemical systems behave in dynamic environments. For example, the study of these reactions has led to better insights into biological systems, like the rhythms and cycles that occur in living organisms. Some scientists even use the BZ reaction to model the complex chemical cycles that power the human heart, breathing rhythms, and other biological functions. Despite its beauty, the BZ reaction is not without its risks. The chemicals involved in the reaction, such as bromine, are toxic, and their fumes can be hazardous. Special care must be taken when conducting this reaction in the laboratory. Ultimately, the Belousov-Zhabotinsky reaction illustrates how chemical reactions are not just about producing a product. They can also be about patterns, rhythms, and behaviors that go far beyond the typical expectations of simple chemistry. It's a reminder that science is full of surprises, even in the world of atoms and molecules. Phosphorus. Burning in water, the fire that defies nature. Phosphorus is a chemical element that defies expectations in many ways, but perhaps none as surprising as its ability to burn in water. White phosphorus, in particular, reacts with water in a spectacularly unexpected manner. It ignites when exposed to the liquid. This phenomenon seems to violate a fundamental principle of chemistry. Fire needs oxygen, and water usually smothers flames. But white phosphorus doesn't follow this rule. When white phosphorus comes into contact with water, a highly exothermic reaction takes place. Phosphorus reacts with the water to produce phosphoric acid and release heat. The heat generated by this reaction is so intense that it ignites the phosphorus, causing it to burn even in the presence of water. The resulting flames are bright and can cause severe burns upon contact. This behavior is unique to white phosphorus. Unlike other types of phosphorus, such as red or black phosphorus, white phosphorus is highly reactive due to its molecular structure. White phosphorus consists of P4 tetrahedra, which are unstable and eager to react with almost anything, including water. This makes white phosphorus incredibly dangerous to handle, as it can burn spontaneously in air or react violently when exposed to moisture. The reaction of phosphorus burning in water is an example of how chemistry is full of surprises. It demonstrates the importance of understanding chemical properties and how they can lead to unexpected outcomes. It also showcases how certain elements have unique and unpredictable behaviors when exposed to different environments. The ability of white phosphorus to burn in water has been used in several practical applications, such as in the production of incendiary devices during wartime. The intense heat generated by the reaction makes it a useful tool for creating fires in challenging conditions. However, its use is highly regulated today due to its dangerous and harmful effects. This phenomenon is also a reminder of the importance of understanding the materials we work with. White phosphorus, when not handled properly, can cause significant harm to people and the environment. This highlights the need for appropriate safety protocols in the laboratory and in industrial settings to prevent accidental combustion or exposure. Despite its hazardous nature, the behavior of white phosphorus is a fascinating example of how chemistry can produce unexpected and awe-inspiring results. The fact that something can burn in water challenges our basic understanding of fire and combustion, making it an intriguing topic of study and an unforgettable example of the power of chemistry. These reactions, along with others in this video, showcase how chemistry can surprise, challenge, and even defy our expectations. Each of these reactions illustrates an important lesson in the unpredictability of chemical interactions, and they help us appreciate the complexity and beauty of the world at the molecular level. Would you like me to continue with more reactions or focus on any other particular type of chemistry topic? The reaction between sodium and water. Sodium is a soft, silvery metal that belongs to the alkali family and is known for its high reactivity. When a small piece of sodium is introduced into water, a vigorous reaction occurs. The metal quickly loses an electron, transforming into sodium ions as it interacts with the water molecules. In this process, water molecules break apart and hydrogen gas is released. The reaction produces sodium hydroxide, a caustic compound, along with the effervescent hydrogen gas. This release of hydrogen creates bubbles that rapidly rise to the surface, sometimes accompanied by audible sizzling sounds. The reaction is exothermic, meaning it releases a great deal of heat in a very short time. This sudden burst of energy can cause the sodium to melt and, in many cases, ignite the hydrogen gas that is evolved. As a result, one often witnesses a bright, almost explosive flame. The visual display is both dangerous and fascinating. The molten sodium may be seen skittering on the water surface as it burns with a yellow-orange light. This characteristic flame is a hallmark of the reaction and serves as a dramatic reminder of the metal's reactivity. Historically, this reaction has been a popular demonstration in chemistry classes. It illustrates fundamental concepts such as electron transfer and exothermic reactions, while captivating audiences with its intensity. Due to the high risk involved, it is performed only in controlled, small-scale experiments. Safety is of utmost importance when dealing with sodium in water. Chemists store sodium in oil to prevent accidental contact with moisture, and experiments are conducted under strict safety protocols to manage the explosive potential and caustic byproducts. Ultimately, the reaction between sodium and water not only teaches us about chemical reactivity and energy release, but also reminds us of the unpredictable power inherent in even the simplest substances. It remains a vivid example of how a small metal can produce dramatic and life-altering effects when exposed to the right conditions. The thermite reaction. The thermite reaction is a dramatic chemical process that involves the reaction of a metal oxide with aluminum powder. In this reaction, aluminum acts as a reducing agent, displacing the metal from its oxide. For example, when iron oxide reacts with aluminum, molten iron is produced alongside aluminum oxide. This reaction is highly exothermic, releasing immense heat that can exceed 2000 degrees Celsius. The high temperature is sufficient to melt metals like iron, which is why the reaction is used in welding and metal cutting applications. The process creates a brilliant display of light and heat. During the reaction, the mixture of iron oxide and aluminum powder is ignited, often with a spark or flame. Once the reaction begins, the aluminum quickly reduces the iron oxide, resulting in the formation of molten iron that flows out like liquid metal. The aluminum oxide forms as a white powdery residue that is left behind. The thermite reaction is a powerful demonstration of oxidation-reduction chemistry. It exemplifies how energy stored in chemical bonds can be released suddenly, resulting in a powerful thermal event. The reaction's intensity has been harnessed for practical uses, including the repair of railway tracks and in incendiary devices. Because of its extremely high temperature and rapid energy release, the thermite reaction must be conducted with great caution. Protective equipment and remote handling techniques are essential to ensure the safety of those involved in the experiment. Its potential for both industrial application and scientific demonstration makes it a subject of ongoing interest. In educational settings, the thermite reaction is used to illustrate the principles of chemical thermodynamics and redox reactions. It provides a striking visual and practical example of how chemical energy is converted into heat and light, capturing the imagination of students and professionals alike. Ultimately, the thermite reaction stands as a testament to the raw power of chemical transformations. It not only reveals the intricate balance of oxidation and reduction, but also challenges our perception of energy release in chemical systems. This reaction remains one of the most visually and conceptually impressive demonstrations in chemistry. The reaction between potassium and water. Potassium, an alkali metal even more reactive than sodium, produces a violent reaction when it comes into contact with water. Upon contact, potassium rapidly loses an electron, forming potassium ions that interact with water to create potassium hydroxide. This process liberates hydrogen gas in large quantities. The reaction is extremely exothermic, releasing enough heat to melt the potassium metal almost instantly. As the metal melts, it forms a glowing molten droplet that dances on the water's surface. The intense heat also causes the hydrogen gas to ignite, resulting in a characteristic lilac or purple flame that is unique to potassium. This explosive reaction is a clear demonstration of the reactivity of alkali metals. The rapid release of hydrogen gas, combined with the significant amount of heat, can lead to an explosion if the reaction is not carefully controlled. In laboratory demonstrations, only a very small amount of potassium is used to ensure safety. The visual spectacle of potassium reacting with water is both dangerous and captivating. Observers may see a flash of violet light, the sound of sizzling, and the rapid movement of liquid metal across the surface of the water. This dynamic interplay of light, heat, and gas illustrates the fundamental principles of chemical reactivity. Due to its volatility, potassium is usually stored under oil to prevent it from coming into contact with moisture. Handling it requires strict safety precautions and specialized equipment, which underscores the importance of understanding chemical hazards in practical applications. This reaction has historical significance, as it helps scientists understand the properties of alkali metals and the nature of exothermic reactions. It serves as a vivid reminder of how even small amounts of reactive materials can produce powerful and sometimes dangerous effects. In summary, the reaction between potassium and water highlights the extreme reactivity of alkali metals. It provides an important educational example of electron transfer, energy release, and the hazards inherent in chemical reactions. The dramatic visual and auditory cues of this reaction continue to fascinate and educate students and researchers alike. The reaction between chlorine and sodium. When chlorine gas comes into contact with sodium metal, a highly energetic reaction occurs that forms sodium chloride. Sodium, a reactive metal, readily loses an electron to form sodium ions, while chlorine, a halogen, gains that electron to become chloride ions. The resulting ionic bond creates sodium chloride, a compound more commonly known as table salt. This reaction is a prime example of a halogen displacement reaction, where a metal reacts with a nonmetal to form an ionic compound. The process releases a considerable amount of heat, making it an exothermic reaction. Often, a bright flash of light accompanies the reaction as the sodium burns with a distinctive yellow flame. The visual aspect of this reaction is particularly striking. As sodium reacts with chlorine, the bright yellow glow of burning sodium contrasts with the greenish-yellow color of chlorine gas. The sodium chloride that forms appears as a white crystalline substance, providing a dramatic transformation from raw elements to a stable compound. Historically, the reaction between sodium and chlorine has played an important role in industrial chemistry. Sodium chloride is essential for life and is widely used in food preservation, chemical manufacturing, and various industrial processes. The reaction also illustrates how reactive elements combine to form compounds with entirely new properties. Safety is paramount when working with chlorine gas, which is toxic and can cause respiratory problems. The reaction is typically conducted in well-ventilated environments or specialized laboratories designed to handle hazardous gases. Proper protective equipment is necessary to prevent inhalation or contact with chlorine. The sodium and chlorine reaction has educational value as well. It is often demonstrated in chemistry classes to illustrate the concepts of ionic bonding, oxidation reduction, and energy release during chemical reactions. Such demonstrations help students understand the dynamic nature of chemical interactions. In essence, the reaction between chlorine and sodium is not only a visually dramatic example of chemical synthesis, but also a fundamental demonstration of how elements combine to create the compounds that are essential to our everyday lives. It reminds us of the transformative power of chemistry and the intricate relationships between elements in the periodic table. The reaction between copper and oxygen. Copper, known for its distinctive reddish color and durability, undergoes a chemical reaction when exposed to oxygen. Over time, copper reacts with the oxygen in the air to form copper oxide, a process commonly known as oxidation. This reaction is responsible for the greenish patina that forms on copper structures and statues, such as the Statue of Liberty. The oxidation of copper begins when the metal surface interacts with atmospheric oxygen and moisture. Initially, a thin layer of copper oxide forms, which is typically black or dark brown in color. As the reaction continues, this oxide layer can transform into other compounds like basic copper carbonate, which gives the patina its characteristic green hue. This reaction is a slow process that unfolds over months or years, yet it serves as a powerful illustration of how chemical reactions occur continuously in the natural environment. The transformation of copper into copper oxide and further into carbonate compounds is an example of a corrosion process that, while it may seem destructive, actually protects the underlying metal from further rapid deterioration. In industrial and artistic contexts, controlled oxidation of copper is sometimes used to achieve a desired aesthetic effect. Artists and architects may deliberately expose copper surfaces to the elements to develop a natural patina that enhances the appearance of the metal. This reaction, though seemingly simple, underscores the dynamic relationship between a material and its environment. From a chemical standpoint, the reaction involves the transfer of electrons from copper atoms to oxygen molecules. This electron transfer leads to the formation of copper ions and oxide ions, which combine to form the various copper oxide compounds. The reaction is an example of redox reduction-oxidation chemistry, where oxidation and reduction occur simultaneously. Environmental factors such as humidity, temperature, and the presence of pollutants can accelerate or modify the oxidation process. For instance, acidic conditions can speed up corrosion, while a stable environment may allow the protective oxide layer to form slowly. This variability makes the study of copper oxidation both complex and fascinating. Ultimately, the reaction between copper and oxygen provides insight into how materials interact with their surroundings over time. It is a reminder that even a sturdy metal like copper is subject to the relentless forces of nature, and that chemical processes, though often slow, can lead to dramatic changes in appearance and properties. This interplay of chemistry and time enriches our understanding of both material science and natural processes. The reaction between sulfur and oxygen. Sulfur, an abundant element known for its distinctive yellow color, reacts readily with oxygen when ignited. When sulfur burns in the presence of oxygen, it forms sulfur dioxide, a toxic and pungent gas. This combustion reaction is a classic example of how a non-metal reacts with oxygen, releasing energy in the process. In the reaction, sulfur combines with oxygen molecules to produce sulfur dioxide. The process is highly exothermic, meaning it releases a significant amount of heat and light. When sulfur is ignited, it burns with a blue flame, and the yellow sulfur quickly transforms into a colorless or slightly bluish gas. The production of sulfur dioxide has important implications in both industry and the environment. Sulfur dioxide is used in the manufacture of sulfuric acid, one of the most widely produced industrial chemicals. However, it is also a major contributor to acid rain, which can have harmful effects on ecosystems, buildings, and human health. In addition to its industrial applications, the reaction between sulfur and oxygen is a subject of environmental concern. The release of sulfur dioxide from industrial processes and volcanic eruptions can lead to widespread air pollution. Once in the atmosphere, sulfur dioxide reacts further to form sulfuric acid droplets, which are responsible for acid rain. This reaction is also an example of combustion in nonmetallic elements. Unlike metals, which often require higher temperatures to react with oxygen, sulfur ignites relatively easily. This property makes sulfur useful in matches and fireworks, where a controlled combustion reaction is desirable for producing light and heat. Safety is a critical consideration when working with burning sulfur and sulfur dioxide. The toxic nature of sulfur dioxide means that proper ventilation and protective gear are essential during experiments or industrial processes. Despite its hazards, the reaction serves as a powerful educational tool for understanding oxidation and combustion in nonmetal elements. Ultimately, the reaction between sulfur and oxygen highlights the dual nature of many chemical processes. While they can be harnessed for useful industrial applications, they may also pose significant environmental and health risks. The delicate balance between these benefits and risks continues to be a central theme in environmental chemistry and industrial practices. The reaction between hydrogen and oxygen. At the molecular level, two molecules of hydrogen react with one molecule of oxygen to yield two molecules of water. This reaction is balanced and simple, yet its implications are profound. The energy released in the process is harnessed in hydrogen fuel cells, which offer a clean source of power for vehicles and other technologies. The reaction is a cornerstone of sustainable energy research. The combustion of hydrogen and oxygen also serves as the fundamental principle behind rocket propulsion. In rocket engines, the controlled explosion of hydrogen and oxygen generates thrust, propelling rockets into space. The efficiency and power of this reaction make it an essential component of modern space exploration. Safety concerns are paramount when working with hydrogen, a gas that is extremely flammable. Even a small spark can trigger the reaction, resulting in a powerful explosion. As such, experiments involving hydrogen and oxygen are conducted under highly controlled conditions with strict safety protocols. The reaction also demonstrates the principle of energy conversion in chemical processes. The chemical bonds in hydrogen and oxygen molecules contain stored energy, which is released when new bonds form to create water. This conversion from chemical energy to heat and light is a central concept in thermodynamics and energy science. In educational settings, The hydrogen-oxygen reaction is often showcased as a dramatic demonstration of chemical energy release. Students observe the powerful reaction and learn about concepts such as stoichiometry, exothermic reactions, and the conservation of energy in chemical transformations. Ultimately, the reaction between hydrogen and oxygen is a vivid illustration of how simple molecules can combine to produce substantial energy. It not only underpins essential technologies like fuel cells and rocket engines, but also serves as an accessible gateway into understanding the principles of combustion and energy conversion in chemistry. The reaction between hydrogen and oxygen is a quintessential example of a combustion reaction, where two highly flammable gases combine to form water. This reaction is famously exothermic, releasing an enormous amount of energy in the form of heat and light. When a mixture of hydrogen gas and oxygen gas is ignited, it reacts rapidly to form water vapor, often with a spectacular explosion. The reaction between potassium permanganate and glycerol. When potassium permanganate reacts with glycerol, an astonishing and visually spectacular reaction unfolds. Potassium permanganate is a strong oxidizing agent, while glycerol is a common viscous alcohol. When these two substances come together, the reaction is highly exothermic, releasing intense heat and producing a burst of flame and light. In this reaction, the potassium permanganate oxidizes the glycerol, causing a rapid chemical transformation. The mixture, initially dark purple due to the potassium permanganate, quickly changes in appearance as the reaction proceeds. As the oxidation continues, the energy released is sufficient to ignite the glycerol, creating bright, dancing flames that captivate onlookers. The reaction is often used in chemistry demonstrations to illustrate the power of oxidation reactions and the dramatic release of energy. It provides a striking example of how a strong oxidizer can cause an organic compound to combust. The flames generated are not only beautiful, but also serve as a powerful educational tool, highlighting concepts of redox chemistry. Safety is critical when performing this reaction. The intense heat and open flame can be dangerous if not handled properly. Laboratory demonstrations require strict safety protocols, including the use of protective gear and proper ventilation. The reaction, while controlled in a demonstration setting, underscores the potential hazards of handling strong oxidizers and combustible organic materials. The chemistry behind the reaction involves the transfer of oxygen from the potassium permanganate to the glycerol. This process leads to the breakdown of the glycerol molecules and the formation of various oxidation products, along with the release of energy. The reaction is a vivid example of how energy stored in chemical bonds can be suddenly released through oxidation. The dramatic nature of the reaction makes it a favorite in educational demonstrations. It not only captures the audience's attention with its intense visual display, but also reinforces fundamental chemical principles, such as oxidation-reduction reactions and energy release in exothermic processes. In conclusion, the reaction between potassium permanganate and glycerol stands as one of chemistry's most memorable demonstrations. It is a testament to the power of oxidation reactions and a vivid illustration of the dramatic energy transformations that can occur when chemicals interact. This reaction continues to inspire and educate, offering both beauty and a deep insight into the nature of chemical energy. The reaction between hydrogen peroxide and potassium iodide. During the reaction, hydrogen peroxide oxidizes the iodide ions from potassium iodide into iodine. The iodine then quickly reacts with starch present in the solution, forming a deep blue complex. The visual transformation from clear to deep blue is striking and occurs after a certain delay, which is why the reaction is often called a clock reaction. This delay allows observers to predict approximately when the color change will occur. The reaction is not instantaneous. It is controlled by reaction kinetics. Factors such as temperature, concentration, and the presence of a catalyst influence the rate at which iodine is produced. This delay is both scientifically significant and visually captivating, providing a clear demonstration of how reaction rates can be manipulated and observed. Scientists and educators use this reaction as an excellent demonstration of chemical kinetics and the role of catalysts in accelerating chemical reactions. The iodine clock reaction vividly shows how a seemingly simple mixture can transform dramatically over time, challenging our expectations of a steady, continuous process. Safety considerations are important, although the reaction is relatively benign compared to more explosive reactions. Care is taken to ensure that the solutions are handled correctly, and that any iodine produced is managed safely. The reaction provides an engaging, hands-on example of chemical change, which is why it is a staple in many educational laboratories. The reaction also highlights the interplay between different chemical species. The formation of the blue iodine starch complex is not merely a byproduct, but a key indicator of the underlying redox reaction. It transforms an invisible chemical process into a visible, dramatic event that can be easily observed and measured. Ultimately, the reaction between hydrogen peroxide and potassium iodide is a powerful educational tool. It elegantly combines concepts of oxidation reduction, reaction kinetics, and catalysis into one engaging demonstration. The resulting iodine clock reaction remains a favorite example in chemistry classes, captivating students with its timing and vivid color change. The reaction between zinc and hydrochloric acid. When zinc metal comes into contact with hydrochloric acid, a classic displacement reaction occurs. Zinc, being a relatively reactive metal, donates electrons to the hydrogen ions in the acid. As a result, zinc is oxidized to form zinc chloride, and hydrogen gas is released. This reaction is a straightforward example of how metals interact with acids. The reaction is exothermic, releasing heat as it proceeds. As zinc dissolves in the acid, small bubbles of hydrogen gas are produced. These bubbles provide a visual cue that the reaction is occurring, and they often rise rapidly to the surface of the solution. The overall reaction is both elegant and simple, demonstrating key principles of chemical reactivity. The chemical process involves the transfer of electrons from zinc atoms to hydrogen ions. This electron transfer results in the formation of positively charged zinc ions and the reduction of hydrogen ions to hydrogen gas. The process is an example of oxidation reduction, or redox chemistry, where one species is oxidized and another is reduced. Historically, the reaction between zinc and hydrochloric acid has been widely used in laboratory experiments. It serves as a reliable method for generating hydrogen gas in a controlled manner. Additionally, the formation of zinc chloride is an important industrial process used in various chemical syntheses and applications. Safety measures are important during this reaction. Hydrochloric acid is corrosive and can cause severe burns, while the hydrogen gas produced is highly flammable. Proper protective equipment and ventilation are necessary to conduct the reaction safely. Despite these hazards, the reaction is valued for its clarity and educational value. This reaction has been a staple in chemistry education, illustrating how metals displace hydrogen from acids. It reinforces fundamental concepts such as reactivity, electron transfer, and redox reactions, providing a foundation for more complex chemical studies. In summary, the reaction between zinc and hydrochloric acid is a classic demonstration of basic chemical principles. It combines the elegance of a simple electron transfer with the practical importance of hydrogen gas production and salt formation. The reaction continues to serve as an important educational tool, reminding us of the fundamental interactions that govern chemical behavior. The reaction between calcium and water. Initially, when calcium is added to water, it slowly dissolves as it reacts with the water molecules. The calcium atoms lose electrons to form calcium ions, which combine with hydroxide ions from water to create calcium hydroxide. Meanwhile, hydrogen gas is liberated as a byproduct of this oxidation process. The reaction does not produce an explosive flame like the reactions of sodium or potassium, but it does generate observable effervescence. Bubbles of hydrogen gas form steadily, creating a gentle fizz that indicates the reaction is underway. The heat produced is sufficient to slightly warm the water, though it is not as dramatic as in more reactive metal-water interactions. Calcium hydroxide, the product of this reaction, is a slightly soluble compound that forms a milky suspension in water. Known commonly as slaked lime, it has many practical uses, including in construction, agriculture, and water treatment. This transformation from a metallic element to a useful compound illustrates the practical side of chemical reactions. The reaction is an example of redox chemistry in a relatively mild form. Although calcium is less reactive than alkali metals, it still undergoes oxidation when in contact with water. This controlled reaction is often demonstrated in educational laboratories to illustrate the gradual nature of some metal-water interactions. Due to the less vigorous nature of the reaction, calcium and water experiments are typically safer to perform than those with sodium or potassium. However, proper safety protocols must still be followed, especially because hydrogen gas is flammable and calcium hydroxide can be caustic. In conclusion, the reaction between calcium and water provides a gentle yet instructive example of metal reactivity. It demonstrates how even less reactive metals participate in oxidation reactions, yielding compounds with significant practical applications. This reaction enriches our understanding of chemical behavior and the wide variety of ways elements interact with water. The reaction between magnesium and hydrochloric acid. Magnesium, a lightweight and silvery metal, reacts readily with hydrochloric acid. When magnesium is added to hydrochloric acid, it displaces hydrogen from the acid, forming magnesium chloride and releasing hydrogen gas. This reaction is well known for its brisk and vigorous nature, though it is typically less explosive than reactions involving more reactive metals. At the outset, magnesium begins to dissolve in the acid as it loses electrons, transforming into magnesium ions. These ions quickly combine with chloride ions from the acid to form magnesium chloride, a soluble salt. The reaction produces bubbles of hydrogen gas that escape from the solution, signifying the progress of the chemical transformation. The reaction is exothermic, releasing a moderate amount of heat that may warm the solution noticeably. While the reaction is energetic, it is generally controlled enough to be safely demonstrated in a laboratory setting. The hydrogen gas produced is flammable, so care must be taken to avoid any sources of ignition during the experiment. Magnesium and hydrochloric acid reactions are popular in educational demonstrations because they clearly illustrate the concept of metal displacement. This reaction provides insight into oxidation reduction processes where magnesium is oxidized and hydrogen is reduced. It is a classic example of how elements can be transformed into entirely new compounds through the transfer of electrons. The resulting magnesium chloride is used in various industrial applications, such as in the production of magnesium metal and as a de-icing agent. Its formation from the reaction also has applications in analytical chemistry, where it serves as a reference for quantitative analysis. Safety is important when handling hydrochloric acid and reactive metals like magnesium. Proper protective gear, including gloves and eye protection, is essential to prevent contact with corrosive substances. Despite these precautions, The reaction is considered a safe and instructive demonstration for students learning the basics of chemistry. In summary, the reaction between magnesium and hydrochloric acid is a dynamic and educational example of chemical reactivity. It encapsulates the principles of oxidation and reduction, while also highlighting the practical applications of the products formed. This reaction serves as a gateway to understanding more complex chemical processes and the fundamental nature of acid-base interactions. The reaction between aluminum and copper sulfate. When aluminum metal is introduced into a solution of copper sulfate, a striking displacement reaction takes place. In this reaction, aluminum is a more reactive metal than copper, and it displaces copper from the copper sulfate compound. As a result, aluminum sulfate is formed, and copper metal is deposited as a solid, often seen as a reddish or brownish coating on the surface of the aluminum. The reaction begins when the aluminum metal comes into contact with the copper sulfate solution. Aluminum atoms lose electrons and form aluminum ions, which then react with the sulfate ions present in the solution. Meanwhile, copper ions, having accepted electrons from the aluminum, are reduced to copper metal. This process is a clear demonstration of redox chemistry, where one substance is oxidized and another is reduced. The deposition of copper onto the aluminum surface is visually impressive. Over time, you may observe a shiny layer of copper forming on the aluminum, while the solution gradually loses its blue color, the characteristic color of copper sulfate. This color change serves as an indicator of the reaction's progress and is a favorite demonstration in chemistry classes. This displacement reaction is not only visually appealing, but also illustrates the activity series of metals. The activity series is a ranking of metals based on their reactivity, and in this case, aluminum's higher reactivity allows it to displace copper from its compound. This concept is fundamental in understanding the behavior of metals in various chemical reactions. The reaction also has practical applications in the field of metallurgy and electrochemistry. It is used in processes such as metal plating and recycling, where unwanted metals are removed from solutions. Understanding this reaction helps chemists control the deposition of metals for industrial purposes. Safety precautions are necessary when working with copper sulfate and aluminum. Although the reaction is relatively safe under controlled conditions, both chemicals can be harmful if mishandled. Protective equipment and proper disposal methods are essential to ensure a safe laboratory environment. In conclusion, the reaction between aluminum and copper sulfate is an engaging demonstration of chemical displacement. It illustrates important concepts such as the activity series, redox reactions, and the visual cues of chemical change. This reaction not only captivates the eye, but also deepens our understanding of the underlying principles that govern metal reactivity. The reaction of iron with oxygen, rusting. Rusting is a slow, naturally occurring oxidation process that affects iron when it is exposed to oxygen and moisture. When iron is left in an environment with air and water, it gradually forms iron oxide, a compound commonly known as rust. This process, though not as dramatic as an explosion, is fascinating in its own right due to its pervasive impact on the durability of metals. Initially, iron reacts with oxygen to form iron oxide, which may appear as a reddish-brown coating on the surface of the metal. The presence of water accelerates this reaction by dissolving the oxygen and facilitating the transport of ions. Over time, the rust spreads and can eventually compromise the structural integrity of the iron, leading to flaking and weakening. The process of rusting is a classic example of corrosion, a chemical reaction where a metal deteriorates as it forms compounds with elements from its environment. This slow oxidation reaction is influenced by factors such as humidity, temperature, and the presence of salts or acids, all of which can accelerate the formation of rust. Rusting has significant implications in both industry and everyday life. It can lead to the failure of bridges, buildings, and vehicles if not properly managed. Engineers and chemists work diligently to develop protective coatings, galvanization techniques, and corrosion inhibitors to slow down the rusting process and extend the lifespan of iron-based materials. On the molecular level, rusting is an electrochemical process. It involves the transfer of electrons from iron to oxygen, facilitated by the presence of water. This gradual electron transfer results in the formation of various iron oxides, each with distinct chemical compositions and physical properties. Understanding these processes is key to developing better anti-corrosion strategies. Despite its slow pace, rusting serves as a powerful reminder of the relentless nature of chemical change. The gradual degradation of iron underscores the continuous influence of environmental factors on materials, and it invites us to consider the broader implications of oxidation in both natural and engineered systems. In summary, the rusting of iron is more than just a nuisance. It is a complex, ongoing chemical process that affects the very fabric of our built environment. By studying rusting, we gain insight into the principles of corrosion and oxidation, learning how to better protect materials and manage the inevitable march of chemical change. The reaction between ammonia and hydrochloric acid. When ammonia gas meets hydrochloric acid, a fascinating acid-base reaction occurs that results in the formation of ammonium chloride. In this reaction, ammonia, a weak base, reacts with the strong acid hydrochloric acid to produce a white solid, a fine powdery salt, known as ammonium chloride. This transformation is both visually striking and chemically significant. The reaction begins as ammonia molecules, which are basic in nature, come into contact with hydrochloric acid vapors or solution. The ammonia molecules accept a proton from the hydrochloric acid, forming ammonium ions. These ammonium ions then combine with chloride ions derived from the acid to form ammonium chloride. The salt precipitates out as a white crystalline solid. One of the remarkable features of this reaction is its rapid and visible nature. In many laboratory demonstrations, the formation of ammonium chloride is accompanied by a sudden appearance of dense, white smoke or fog. This smoke is actually tiny crystals of the salt, forming almost instantaneously as the gases react. The reaction is reversible under certain conditions. If the temperature is raised, the ammonium chloride can decompose back into ammonia and hydrochloric acid. This dynamic equilibrium illustrates important principles of chemical equilibrium and the effects of temperature on reaction rates. It serves as an excellent example of how a chemical reaction can be shifted by external conditions. In educational contexts, the ammonia and hydrochloric acid reaction is widely used to demonstrate acid-base reactions, gas phase reactions, and precipitation. It helps students visualize the interplay between gaseous reactants and solid products, as well as understand the concept of reversibility in chemical reactions. Safety is relatively straightforward with this reaction, though care must be taken to avoid inhaling the dense ammonium chloride vapor. The reaction is generally safe in well-ventilated spaces, making it ideal for classroom demonstrations that captivate students with both its visual and chemical intrigue. Ultimately, the reaction between ammonia and hydrochloric acid is a classic example of an acid-base reaction that is both educational and dramatic. It reveals the fundamental nature of chemical interactions and the way that simple gases can combine to form solid, tangible substances, offering deep insights into the world of chemistry. The reaction between sodium bicarbonate and vinegar. When sodium bicarbonate reacts with vinegar, an everyday acid, a classic acid-base reaction takes place that results in the formation of carbon dioxide gas, water, and sodium acetate. This reaction is familiar to many as the source of bubbling and fizzing in common household mixtures. It serves as a perfect demonstration of chemical reactions in action using items that can be found in most kitchens. The reaction begins when sodium bicarbonate, a base often known as baking soda, is mixed with vinegar, which contains acetic acid. The acid reacts with the bicarbonate ion, releasing carbon dioxide gas as a byproduct. This gas forms bubbles that rapidly escape from the liquid, producing the characteristic fizzing and foaming. The production of carbon dioxide is not only visually appealing, but also illustrates the principle of gas evolution in chemical reactions. As the gas is released, it can cause pressure to build up in a confined space. This principle is sometimes used in simple experiments to inflate a balloon or to demonstrate the release of energy from a chemical reaction. This reaction is exothermic to a small degree, meaning it releases a tiny amount of heat. However, the primary visual effect is the vigorous bubbling and expansion caused by the escaping carbon dioxide. The reaction is simple, yet robust, making it a favorite in educational settings to illustrate basic chemical principles. In addition to its educational value, the reaction between sodium bicarbonate and vinegar has practical applications in cooking, cleaning, and even in some forms of pest control. It is the basis for many baking recipes where the carbon dioxide generated helps dough to rise. Its cleaning properties are also widely utilized, as the fizzing action can help dislodge grime and dirt. Safety is minimal for this reaction, making it ideal for classroom demonstrations and home experiments. The chemicals involved are common and non-toxic in the quantities used, which allows for hands-on exploration without significant risk. This accessibility makes the reaction a perfect starting point for introducing basic chemical concepts. In conclusion, the reaction between sodium bicarbonate and vinegar is a delightful demonstration of everyday chemistry. It combines simple ingredients to produce an immediate, observable effect, bridging the gap between chemical theory and everyday experience. This reaction remains a staple in chemistry education, celebrated for its simplicity, safety, and engaging visual display. The reaction of nitric acid with copper. When nitric acid reacts with copper metal, a striking and vigorous reaction occurs that produces copper nitrate, nitrogen dioxide, and water. In this reaction, nitric acid serves as a strong oxidizing agent, and copper, a relatively unreactive metal, is oxidized to form copper ions. These ions then combine with nitrate ions to form copper nitrate, a blue-green solution, while nitrogen dioxide gas is liberated as a reddish-brown vapor. The reaction begins when copper is immersed in concentrated nitric acid. The nitric acid oxidizes the copper, causing it to dissolve gradually. As the reaction proceeds, nitrogen dioxide, a toxic and corrosive gas, is evolved. The release of this brown gas provides a clear visual cue of the reaction's progress. The chemical process involves several intermediate steps. Nitric acid not only oxidizes the copper, but also undergoes a reduction process itself, which leads to the formation of nitrogen dioxide. The overall reaction is highly exothermic, meaning that it releases heat. In controlled conditions, the reaction can be quite rapid and energetic, often used in demonstrations of acid-metal reactions. The formation of copper nitrate is accompanied by a color change in the solution. The blue-green color of the copper nitrate is a distinctive marker of the reaction, and it contrasts sharply with the color of the original nitric acid. This visual transformation makes the reaction a favorite demonstration in chemistry classes to illustrate the power of oxidation and reduction processes. Because the reaction produces nitrogen dioxide, which is both toxic and irritating to the respiratory system, it must be carried out in a well-ventilated area or under a fume hood. Safety protocols are essential to ensure that exposure to the gas is minimized. The reaction also emphasizes the need for careful handling of strong acids and reactive metals. This reaction is not only interesting from a theoretical standpoint, but also has practical implications. Copper nitrate is used in various applications, including as a catalyst in chemical synthesis and in the production of pigments. The reaction demonstrates how raw materials can be transformed into valuable chemical compounds through oxidation. In summary, the reaction between nitric acid and copper provides a dramatic illustration of redox chemistry in action. It combines vivid color changes, the evolution of toxic gases, and significant heat release to create a memorable and instructive chemical process. This reaction stands as a testament to the transformative power of acids in altering the nature of metals and continues to serve as an engaging educational example in the field of chemistry. The reaction between calcium carbide and water. Calcium carbide is a compound that reacts dramatically when it meets water. When a piece of calcium carbide is added to water, it undergoes a hydrolysis reaction that produces acetylene gas and calcium hydroxide. This reaction is highly exothermic, meaning it releases heat rapidly. The heat generated is sufficient to ignite the acetylene gas in air, resulting in a brilliant flame that is often used in welding and cutting applications. The mechanism involves the water molecules attacking the calcium carbide, breaking its strong bonds and liberating acetylene, a gas prized for its combustibility. The overall chemical process transforms a solid into both a gas and a new solid, calcium hydroxide. Industrially, the production of acetylene through this reaction has been pivotal for oxyacetylene welding. The acetylene produced is then mixed with oxygen, and when ignited, it creates a flame that can reach extremely high temperatures. The reaction is not only practical, but also captivating to watch. The sudden fizzing and the appearance of flames are both visually striking and scientifically informative. Safety precautions are essential when performing this reaction because acetylene is highly flammable and the reaction releases significant heat. Laboratories and industrial setups use specialized equipment to control the process safely. Historically, calcium carbide's reaction with water marked a significant milestone in chemical engineering and industrial chemistry, leading to innovations in metalworking and manufacturing. In summary, the reaction between calcium carbide and water is a vivid demonstration of how a simple compound can be transformed into valuable gases and heat, underpinning essential industrial processes and offering a spectacular display of chemical energy. The reaction between sodium thiosulfate and acid. When sodium thiosulfate is mixed with an acid such as hydrochloric acid, a fascinating reaction takes place that results in the formation of sulfur. In this reaction, the acid reacts with sodium thiosulfate to produce sodium sulfate, water, and elemental sulfur. The sulfur precipitates out as a fine cloudy suspension, turning the solution milky white. This dramatic color change is often used in demonstrations because the initially clear solution rapidly becomes opaque as sulfur particles disperse throughout the mixture. The reaction proceeds via a redox process in which the thiosulfate ion is oxidized, while the acid provides protons that facilitate the reaction. The formation of sulfur is key, and its precipitation is what gives the reaction its characteristic appearance. This reaction is a staple in introductory chemistry courses as it visually demonstrates concepts like acid-base chemistry, oxidation-reduction reactions, and precipitation. Due to the rapid formation of sulfur, the reaction also offers insights into nucleation and particle growth in colloidal systems. Observing the transformation provides a tactile sense of how chemicals interact in solution. Safety is relatively straightforward in this demonstration, though appropriate precautions should be taken when handling acids. Overall, The sodium thiosulfate and acid reaction is a classic example of how a chemical process can yield an immediate, visually engaging change, making it a popular subject for both education and demonstration. The reaction between iodine and sodium, thiosulfate, iodine clock reaction variation. In one of the classic demonstrations of chemical kinetics, a solution containing iodine reacts with sodium thiosulfate in a dramatic way. This reaction is often designed as part of the iodine clock experiment, where the timing of a color change is used to illustrate reaction rates. Initially, the solution appears dark due to the presence of iodine. When sodium thiosulfate is added, it reduces iodine to iodide ions. However, the reaction proceeds at a controlled rate, and the disappearance of iodine is not instantaneous. After a certain delay, dictated by the reaction conditions, the remaining iodine reacts with a starch indicator, producing a sudden and striking color change to deep blue. This time delay provides an excellent demonstration of how reaction rates can be manipulated by adjusting concentrations, temperature, or other factors. The iodine clock reaction has captivated students and scientists alike, as it transforms an invisible chemical process into a dramatic visual event. Safety measures for this reaction are moderate, as the chemicals used are generally safe in dilute solutions, though care should be taken to avoid spills. In summary, this variation of the iodine clock reaction illustrates key principles of chemical kinetics and redox reactions, engaging viewers with its timed, vivid color shift and providing a window into the dynamic world of chemical change. The reaction between aluminum and copper sulfate. When aluminum metal is immersed in a solution of copper sulfate, a fascinating displacement reaction occurs. Aluminum, being more reactive, displaces copper from its sulfate compound. This results in the formation of aluminum sulfate and the deposition of elemental copper as a solid on the surface of the aluminum. The reaction is a classic demonstration of the activity series, showing how a more reactive metal can reduce a less reactive metal ion. As the reaction proceeds, the solution gradually loses its blue color, characteristic of copper sulfate, and a reddish deposit of copper appears on the aluminum. This visually striking transformation not only illustrates redox chemistry, but also provides insight into the mechanisms of metal displacement and electron transfer between elements. Industrial applications of this reaction include methods of metal purification and recycling, where such displacement reactions are harnessed for practical use. Safety is important, as the chemicals involved can be corrosive and require proper handling. Protective gear is essential during demonstrations or experiments. Ultimately, the aluminum and copper sulfate reaction is a vivid and educational example of how chemical principles like the activity series operate in real time, offering both visual appeal and scientific depth. The reaction between gold and Aqua Regia. Gold is known for its resistance to corrosion and its inertness. However, when it is introduced to a mixture known as Aqua Regia, a remarkable reaction occurs. Aqua Regia, which means royal water, is a combination of nitric acid and hydrochloric acid. Despite gold's notorious resistance to single acids, Aqua Regia is capable of dissolving gold. The reaction takes place as the nitric acid oxidizes the gold to form gold ions, which then combine with chloride ions from the hydrochloric acid to form chloroauric acid. This reaction is highly prized in the refining and recovery of gold, as it allows for the purification of gold from other metals. The process is a fine example of complex acid chemistry and illustrates how even the most noble metals can be transformed under the right conditions. Visually, the reaction may begin slowly, but then accelerate as gold dissolves, creating a characteristic yellow or orange solution. Due to the strength and corrosiveness of Aqua Regia, The reaction must be carried out with extreme caution, using specialized glassware and proper safety protocols. The ability of Aqua Regia to dissolve gold has significant historical and practical importance, playing a critical role in alchemy and modern metallurgy alike. In conclusion, the gold and Aqua Regia reaction is a striking illustration of how mixtures of strong acids can challenge our expectations about chemical inertness, unlocking valuable insights into the reactivity of noble metals. The reaction between mercury and chlorine. When mercury, a liquid metal at room temperature, is exposed to chlorine gas, a notable reaction occurs that produces mercury, chloride. This reaction is striking because mercury, chloride, forms as a bright crystalline solid that is visible against the backdrop of liquid mercury. The process involves the oxidation of mercury by chlorine gas, resulting in mercury ti-ions that immediately combine with chloride ions. Mercury T-chloride, also known as calomel, is historically significant in medicine and chemistry. Its formation is both rapid and exothermic, releasing heat in the process. The visual transformation from shiny, liquid mercury to a solid white compound is dramatic and has been used in laboratory demonstrations to illustrate halogen metal reactions. Because chlorine gas is highly toxic, this reaction is typically carried out in a controlled environment with appropriate ventilation and safety measures. The reaction not only highlights the reactivity of chlorine, but also illustrates how even metals that appear unreactive in certain states can undergo significant changes under the influence of strong oxidizing agents. Ultimately, the mercury and chlorine reaction serves as a reminder of the diverse behaviors of metals and nonmetals in chemical reactions, bridging visual spectacle and practical chemical principles. The reaction between sodium hypochlorite and ammonia. When sodium hypochlorite, commonly found in household bleach, is mixed with ammonia, a dangerous and unexpected reaction occurs. This reaction leads to the formation of chloramines, a group of toxic compounds that can cause respiratory problems and other health issues. The process begins with ammonia reacting with sodium hypochlorite to form a variety of chloramine species, depending on the proportions and conditions. This reaction is notorious for its rapid production of fumes that can be harmful if inhaled. Even small amounts of mixing these chemicals in a poorly ventilated area can create a hazardous environment. The chemistry behind this reaction involves the substitution of hydrogen in ammonia with chlorine, yielding compounds that are far more volatile and toxic than the original substances. In industrial settings, great care is taken to avoid the accidental mixing of these chemicals, and strict guidelines are in place to protect workers and consumers. The reaction is often cited as a classic example of how common household chemicals can become dangerous if not used properly. In summary, the reaction between sodium hypochlorite and ammonia is a vivid demonstration of chemical incompatibility, serving as a cautionary tale about the importance of proper chemical handling and safety protocols. The reaction between potassium chlorate and a catalyst. Potassium chlorate is a powerful oxidizing agent that, when combined with a catalyst such as manganese dioxide, decomposes to release oxygen gas rapidly. The reaction is highly exothermic and produces a large volume of oxygen, which can accelerate the combustion of nearby combustible materials. In this reaction, the potassium chlorate breaks down into potassium chloride and oxygen gas. The catalyst lowers the activation energy required for the reaction, causing the decomposition to occur at a much faster rate. This rapid release of oxygen is often used in laboratory demonstrations to illustrate how catalysts work, as well as in practical applications such as oxygen generation in certain industrial processes. The visual display is impressive. A small amount of catalyst added to potassium chlorate can produce vigorous bubbling and a visible surge of gas. Due to its energetic nature, the reaction must be handled with care to avoid uncontrolled explosions. Proper safety measures, including the use of protective barriers and controlled environments, are critical when performing this reaction. The potassium chlorate reaction serves as a clear example of how catalysts can transform a slow reaction into a rapid energetic process by lowering the energy barrier for chemical transformation. Ultimately, this reaction not only demonstrates the concept of catalysis, but also underscores the powerful role of oxidizers in chemical processes, bridging the gap between theoretical principles and practical, observable phenomena. The reaction between magnesium and oxygen, combustion of magnesium. Magnesium is a highly reactive metal known for its brilliant white flame when it burns in oxygen. When magnesium is ignited, it reacts with oxygen in the air to form magnesium oxide, a white powder that is often seen as a residue after combustion. The reaction is extremely exothermic, releasing an enormous amount of heat and light. The flame produced is so bright that it can be used as a signal or in photographic flashes. The chemical process involves magnesium atoms losing electrons to form magnesium ions, which then combine with oxygen to create magnesium oxide. This reaction has practical applications in flares, fireworks, and pyrotechnics, where the intense brightness of burning magnesium is highly valued. Because of the high temperature reached during the reaction, the burning magnesium also serves as an excellent demonstration of energy conversion and exothermic reactions in the classroom. Safety is crucial when working with magnesium, as the intense flame can cause burns and the fine magnesium oxide produced may be harmful if inhaled. In conclusion, the combustion of magnesium and oxygen is a striking and educational reaction that vividly demonstrates the principles of oxidation, electron transfer, and energy release, captivating observers with its brilliant white light. The reaction between tin and hydrochloric acid. Tin, a moderately reactive metal, undergoes a displacement reaction when it comes into contact with hydrochloric acid. In this reaction, tin reacts with hydrochloric acid to form tin, I-chloride, and hydrogen gas. The tin atoms lose electrons to become tin, I ions, while the hydrogen ions from the acid are reduced to form hydrogen gas, which bubbles out of the solution. This process is exothermic, although less dramatically so than some reactions involving more reactive metals. The production of hydrogen gas provides a visible indicator that the reaction is occurring. The resulting tin, I-chloride, is a soluble salt that finds applications in various industrial and chemical processes. It also serves as a useful compound in laboratory experiments to illustrate acid-metal reactions. This reaction provides a clear example of redox processes where tin is oxidized and hydrogen is reduced, reinforcing core chemical principles. While the reaction is relatively gentle compared to others, it still requires careful handling of hydrochloric acid due to its corrosive nature. The reaction has historical significance in metallurgy and chemical synthesis, being one of the ways to transform a metal into a more reactive compound for further processing. Overall, the reaction between tin and hydrochloric acid is a practical demonstration of basic chemical reactivity, offering insight into oxidation, reduction, and the formation of new compounds from simple reactions. The reaction between sulfuric acid and sugar. When concentrated sulfuric acid is mixed with sugar, an astonishing dehydration reaction occurs. In this reaction, sulfuric acid acts as a powerful dehydrating agent, drawing water out of sugar molecules. The result is the formation of a charred black carbon mass as the sugar loses its water and decomposes. The reaction is highly exothermic, releasing heat as it rapidly transforms the crystalline sugar into a foam-like carbon-rich structure. The visual spectacle of the reaction is striking. A mound of sugar dramatically expands and blackens as it converts into pure carbon, often accompanied by a hissing sound as steam is released. This reaction illustrates the powerful dehydrating properties of sulfuric acid, which is capable of breaking down complex organic molecules into their elemental components. It also demonstrates how an acid can drive a chemical transformation that is both physical and chemical in nature, altering the structure and composition of the sugar. Due to the intense heat and corrosive nature of sulfuric acid, safety measures are crucial when performing this experiment. Protective gear and controlled environments are necessary to prevent injury. Ultimately, the reaction between sulfuric acid and sugar provides a dramatic example of chemical dehydration, transforming a common household substance into a visually captivating display of carbon formation and energy release. The reaction between phosphorus pentoxide and water. Phosphorus pentoxide is a powerful dehydrating agent that reacts explosively with water. When phosphorus pentoxide is introduced to water, it undergoes a vigorous exothermic reaction that forms phosphoric acid. The reaction is highly energetic, and the heat released is intense enough to cause splattering and vigorous bubbling. The chemical process involves phosphorus pentoxide absorbing water molecules and converting into orthophosphoric acid, a reaction that illustrates the substance's remarkable affinity for water. This reaction is not only fascinating from a chemical standpoint, but also has significant industrial importance. Phosphoric acid is a valuable commodity in the production of fertilizers, food additives, and various other chemical products. The intense reaction highlights the reactivity of phosphorus pentoxide and the dangers inherent in handling such powerful dehydrating agents. Special care must be taken to control the reaction conditions and prevent injury from the exothermic burst. In educational demonstrations, the reaction is used to show how a solid compound can react violently with water, producing a liquid acid and releasing a great deal of heat. The reaction also offers insights into the principles of hydration and the formation of acids from oxides, a fundamental concept in inorganic chemistry. Ultimately, the reaction between phosphorus pentoxide and water provides a vivid example of chemical transformation and energy release, underscoring the powerful interactions between oxides and water in the formation of acids. The reaction between calcium oxide and water, slaking of lime. Calcium oxide, commonly known as quicklime, reacts exothermically with water in a process known as slaking. When water is added to calcium oxide, it forms calcium hydroxide, also called slaked lime. This reaction is notable for its significant heat release, which can sometimes cause the water to boil or steam vigorously upon contact. The process begins with the rapid hydration of calcium oxide, which leads to the formation of a suspension of calcium hydroxide. As the reaction proceeds, the mixture becomes more uniform, and the heat generated can be both dangerous and useful in industrial applications. The reaction is fundamental in the production of building materials such as mortar and plaster. Slaked lime is used to create a binding agent that holds together the components of these materials. The exothermic nature of the reaction is also a classic demonstration in chemistry classes, where the sudden release of heat illustrates the concept of enthalpy changes in chemical reactions. Safety is important when handling calcium oxide and water together, as the heat produced can cause burns. Proper protective equipment and control conditions are necessary for laboratory experiments. The reaction also serves as an example of how chemical processes can be harnessed for practical applications, transforming a reactive metal oxide into a stable compound with wide-ranging uses. In summary, the reaction between calcium oxide and water is a vivid demonstration of hydration, exothermic reactions, and the practical applications of chemical transformations in construction and industry. The reaction between sodium hypochlorite and acetic acid. When sodium hypochlorite, commonly found in household bleach, is mixed with acetic acid, vinegar, a chemical reaction occurs that produces a mixture of chlorine gas and other compounds. This reaction involves the acid-induced decomposition of sodium hypochlorite, releasing chlorine gas, a highly reactive and toxic substance. The process is a vivid demonstration of acid-base reactions that lead to the formation of gaseous products from liquid reagents. As the acetic acid reacts with sodium hypochlorite, the solution often becomes turbid, and a distinct chlorine odor fills the air, serving as an indicator that the reaction is in progress. The reaction is exothermic, although not explosively so, and it serves as an important cautionary example of why household chemicals should never be mixed without understanding the potential consequences. The formation of chlorine gas in this context is particularly dangerous, as inhalation can lead to respiratory distress and other health hazards. The reaction underscores the need for proper ventilation and safety precautions in any situation where these chemicals might inadvertently mix. This reaction is not only of practical concern, but also serves as a useful educational demonstration. It illustrates how acids can destabilize and decompose oxidizing agents, leading to the release of reactive gases. Furthermore, the reaction highlights the delicate balance between reactivity and stability in common chemical compounds, reminding us that everyday substances can become hazardous under the right conditions. Ultimately, the reaction between sodium hypochlorite and acetic acid is a stark reminder of the potential dangers in our household chemistry, urging careful handling and strict adherence to safety guidelines. The reaction between copper and sulfuric acid, hot concentrated sulfuric acid. When copper is exposed to hot concentrated sulfuric acid, a vigorous reaction occurs that results in the formation of copper sulfate, sulfur dioxide, and water. In this reaction, sulfuric acid acts as a powerful oxidizing agent, oxidizing copper metal into copper ions. These ions then combine with sulfate ions from the acid to form copper sulfate, which is typically a blue solution. The reaction is highly exothermic, and the concentrated acid produces sulfur dioxide gas, a toxic, pungent gas that is released during the process. The production of sulfur dioxide is a clear indicator of the oxidation taking place, as it is a byproduct of the acid's reaction with copper. The visual aspect of the reaction is dramatic. As copper dissolves, the solution changes color, and dense, brownish sulfur dioxide gas is evolved. This serves as an excellent demonstration of the power of concentrated acids in oxidizing metals. Due to the toxicity of sulfur dioxide and the corrosiveness of hot concentrated sulfuric acid, the reaction must be carried out in a fume hood with proper protective equipment. Safety precautions are essential to prevent exposure to harmful vapors. This reaction has historical significance in the field of analytical chemistry and metallurgy, where it has been used to understand the behavior of metals under extreme conditions. In educational demonstrations, the reaction provides a vivid example of redox processes and the chemical behavior of acids when interacting with metals. It serves as a lesson in both chemical reactivity and the importance of safety in handling corrosive substances. In conclusion, the reaction between copper and hot concentrated sulfuric acid is a powerful illustration of how strong oxidizing acids interact with metals, producing striking visual effects and important chemical products, while also underscoring the need for rigorous safety practices. The reaction between silver nitrate and sodium chloride. When silver nitrate and sodium chloride solutions are mixed, a classic precipitation reaction takes place. In this reaction, silver ions from silver nitrate combine with chloride ions from sodium chloride to form silver chloride, an insoluble compound that precipitates as a white, curdy solid. The formation of silver chloride is visually striking. The clear solutions quickly turn milky white as the solid particles form and disperse throughout the mixture. This reaction serves as an excellent demonstration of solubility rules in chemistry and is often used in educational settings to illustrate how ionic compounds interact in solution. The precipitation of silver chloride not only provides a clear visual cue, but also reinforces the concept of chemical equilibrium, as the formation of an insoluble product drives the reaction forward. In addition to its educational value, this reaction has practical applications in qualitative analysis and in photographic processes, where silver halides play a key role in image formation. Safety is relatively straightforward when handling these reagents, though care must be taken as silver compounds can be toxic in larger amounts. Overall, the reaction between silver nitrate and sodium chloride is a classic example of a precipitation reaction that elegantly demonstrates the principles of ionic interactions and solubility in chemistry. The reaction between tin-2 chloride and sodium hydroxide. When tin-chloride reacts with sodium hydroxide, a fascinating precipitation and hydrolysis reaction occurs. In this process, tin-DiOs ions from tin-dichloride interact with hydroxide ions from sodium hydroxide to form tin-dihydroxide, which precipitates out of solution as a white solid. The reaction is a typical example of a double displacement reaction, where ions exchange partners to form new compounds. As the tin-dicyl hydroxide forms, it may further undergo hydrolysis to produce a gelatinous precipitate, which demonstrates the complexity of tin chemistry in aqueous solutions. This process is particularly useful in qualitative analysis, as it helps chemists identify the presence of tin ions in a solution. The distinct appearance of the precipitate serves as a reliable indicator in laboratory tests. The reaction is exothermic, although the heat released is relatively mild compared to more vigorous reactions. The gradual formation of the white precipitate is both visually clear and scientifically instructive. Careful control of the pH is essential in this reaction, as excessive base can lead to redissolution of the precipitate and formation of soluble complexes. This reaction illustrates the delicate balance in chemical systems and highlights the importance of pH in controlling the course of reactions. In summary, the reaction between tin-EE chloride and sodium hydroxide is an instructive example of precipitation, hydrolysis, and the sensitivity of chemical equilibria to changes in conditions. The reaction between sulfur and iron to form iron sulfide. When sulfur and iron react together under heat, they form iron sulfide, a compound with a distinctive dark appearance. In this reaction, elemental sulfur reacts with iron, usually in powdered form, to produce iron sulfide. The process is thermally driven and requires significant heat to overcome the activation energy for the reaction. The formation of iron sulfide is a classic example of a combination reaction where two elements combine to form a compound. The product is typically a dark, sometimes nearly black, solid that marks the successful synthesis of the new substance. This reaction has historical significance in metallurgy and the production of various alloys. Iron sulfide compounds have been used in various industrial processes, including as pigments, and in the production of sulfur dioxide when further oxidized. The reaction is exothermic, releasing heat as the chemical bonds between iron and sulfur are formed. The rapid combination of the two elements illustrates the power of high-temperature reactions in altering the chemical composition of materials. Observing the reaction provides insight into solid-state chemistry and the transformation of elements under extreme conditions. The formation of iron sulfide can also serve as an indicator of how sulfur interacts with metals in various environments, including in geological processes. Safety precautions must be taken when performing this reaction due to the high temperatures required. Proper insulation and protective equipment are essential to prevent burns and other injuries. Overall, the reaction between sulfur and iron to form iron sulfide is a fascinating demonstration of elemental combination and high-temperature chemistry, offering both industrial relevance and scientific intrigue. The reaction between tin and oxygen, oxidation of tin. Tin, a relatively soft metal, undergoes oxidation when exposed to oxygen, forming tin oxide. This reaction is a slow, gradual process that occurs when tin is exposed to the air over time. The tin reacts with atmospheric oxygen to form tin oxide, a compound that typically appears as a dull grayish or white coating on the surface of the metal. The process of oxidation in tin is similar to rusting in iron, though tin oxide is more stable and less detrimental to the metal's integrity. The protective layer of tin oxide can actually prevent further corrosion by acting as a barrier to oxygen and moisture. This reaction is an important example of passivation, where a metal forms a surface layer that protects it from further degradation. Many metals, including aluminum and titanium, exhibit similar behavior, forming oxide layers that preserve their structural integrity. The formation of tin oxide is not accompanied by dramatic heat or explosive reactions, but is instead characterized by a slow and steady transformation. This gradual process offers an excellent opportunity to study the kinetics of oxidation and the factors that influence corrosion. Environmental factors such as humidity, temperature, and the presence of pollutants can accelerate the oxidation of tin. Understanding these factors is crucial in applications such as soldering, where tin-based alloys are used extensively. In industrial settings, controlling the oxidation of tin is important to maintain the quality and performance of tin-coated products. The reaction is also relevant in the study of surface chemistry and the durability of metals. In summary, the oxidation of tin to form tin oxide is a classic demonstration of corrosion and passivation, offering insights into the gradual transformation of metals in everyday environments. The reaction between benzoyl peroxide and organic compounds. Benzoyl peroxide is a widely used organic compound that serves as an initiator for free radical reactions. When benzoyl peroxide decomposes, it produces free radicals that can initiate polymerization or oxidation reactions in organic compounds. This reaction is central to many industrial processes, including the production of plastics, synthetic rubbers, and other polymers. The free radicals generated by benzoyl peroxide are highly reactive and trigger a cascade of chemical reactions that convert monomers into long-chain polymers. The decomposition of benzoyl peroxide is exothermic, meaning it releases heat as it breaks down into smaller radical fragments. This energy release can accelerate the polymerization process, making it a highly efficient initiator in industrial settings. The reaction is carefully controlled by adjusting temperature and concentration to ensure a steady generation of free radicals. If uncontrolled, the rapid formation of radicals can lead to runaway reactions, which are hazardous in both laboratory and industrial environments. Benzoyl peroxide is not only used in polymerization, but also finds application as a bleaching agent and an acne treatment in dermatology. Its ability to generate free radicals allows it to break down complex molecules, providing a basis for its diverse uses. The reaction between benzoyl peroxide and organic compounds provides valuable insights into free radical chemistry, a field that explains many seemingly unpredictable reactions in organic chemistry. It illustrates how free radicals can drive the formation of new chemical bonds and the transformation of simple compounds into complex materials. Safety is paramount when working with benzoyl peroxide due to its explosive potential and sensitivity to heat and light. Proper storage, handling, and controlled conditions are essential to harness its reactivity safely. In summary, the reactions initiated by benzoyl peroxide are critical to modern organic synthesis and industrial chemistry. They demonstrate the power of free radical processes and their applications in creating a wide array of useful products from everyday organic compounds. The reaction between ethanol and acetic acid, esterification. When ethanol, a simple alcohol, reacts with acetic acid, a carboxylic acid, a classic esterification reaction occurs. This reaction produces ethyl acetate and water as products, and it is catalyzed by an acid such as sulfuric acid. Ethyl acetate is a common solvent used in many industries and is known for its sweet, fruity odor. The process begins as the hydroxyl group from ethanol reacts with the carboxyl group from acetic acid, forming a new ester bond. The reaction is reversible, and conditions such as the removal of water or the use of excess reactants are often employed to drive the reaction to completion. Esterification is an important reaction in organic chemistry and is used to synthesize a wide variety of esters, which are compounds with diverse applications in flavorings, fragrances, and solvents. This reaction not only exemplifies the formation of new chemical bonds, but also illustrates principles of equilibrium and catalysis. The acid catalyst speeds up the reaction without being consumed, allowing the process to proceed more efficiently. Educational demonstrations of esterification often include the pleasant aroma of ethyl acetate, which helps to engage students by connecting chemical transformations to sensory experiences. Safety considerations for this reaction are moderate, as both ethanol and acetic acid are relatively safe in controlled laboratory environments. However, proper ventilation and handling procedures are recommended due to the volatile nature of the reactants and products. Overall, the esterification reaction between ethanol and acetic acid is a fundamental organic transformation that reveals the beauty of chemical synthesis, equilibrium dynamics, and catalysis, making it a favorite topic in both academic and industrial chemistry. The reaction between magnesium and hydrochloric acid, alternate approach. Magnesium is a light, silvery metal that reacts with hydrochloric acid in a brisk, energetic manner. When magnesium is added to hydrochloric acid, it dissolves as it forms magnesium chloride and hydrogen gas. This reaction is a classic demonstration of metal displacement, where magnesium displaces hydrogen from the acid. The reaction is exothermic, releasing enough heat to warm the solution and produce visible bubbles of hydrogen gas. The effervescence is a clear indication that the reaction is proceeding, providing a visual cue for the progress of the chemical transformation. Magnesium chloride, the product of this reaction, is a soluble salt that has practical applications in de-icing and in the production of magnesium metal. The hydrogen gas produced is often collected or used as a demonstration of gas evolution. This reaction reinforces core concepts in redox chemistry, highlighting the transfer of electrons from magnesium to hydrogen ions. The process exemplifies how a metal can be oxidized while reducing another species in the solution. Because of its energetic nature, the reaction is commonly demonstrated in chemistry classes to illustrate principles such as stoichiometry, reaction kinetics, and the conservation of mass. Safety protocols are essential, particularly because hydrochloric acid is corrosive and the evolved hydrogen gas is flammable. Proper protective equipment and ventilation ensure that the reaction is conducted safely. In conclusion, the reaction between magnesium and hydrochloric acid is a fundamental example of metal-acid interactions, offering clear visual and practical evidence of redox processes and the energetic nature of chemical reactions. The reaction between iron and sulfur, formation of iron sulfide. When iron powder is mixed with sulfur and heated, they react to form iron sulfide, a compound with significant industrial and geological importance. The reaction begins with the intimate mixing of fine iron particles and sulfur. Upon heating, the two elements react vigorously, with sulfur combining with iron to produce iron sulfide. The product typically appears as a dark, brittle solid that is distinctly different from the original reactants. This reaction is an example of a combination reaction, where two elements chemically bond to form a new compound. The process is exothermic, releasing heat as the chemical bonds form, and the structure of iron sulfide is created. The formation of iron sulfide has practical applications in the production of pigments, as well as in understanding natural processes such as the formation of ore deposits. In geological contexts, the reaction provides insights into how sulfide minerals are formed in the Earth's crust. The reaction also illustrates the principles of thermodynamics and kinetics, as the rate and extent of the reaction can be influenced by factors such as temperature, particle size, and mixing efficiency. Safety considerations include proper handling of fine powders and the careful control of temperature to avoid accidental ignition or excessive reaction rates. The process is often demonstrated in laboratories to show how simple elements combine under heat to form more complex compounds. It offers a clear example of exothermic reactions and the transformation of raw elements into industrially useful materials. In summary, the reaction between iron and sulfur to form iron sulfide is an illuminating example of combination reactions, bridging laboratory demonstrations with geological and industrial applications, and showcasing the dynamic nature of chemical bonding. The reaction between ethylene and hydrogen, hydrogenation. Hydrogenation is an important chemical reaction in which unsaturated compounds, such as ethylene, react with hydrogen gas to form saturated compounds. In the hydrogenation of ethylene, the double bond between carbon atoms is broken, and hydrogen atoms are added to form ethane. This reaction typically requires a catalyst, such as nickel or platinum, to proceed at a practical rate. The process is exothermic, releasing heat as the unsaturated bonds are replaced by single bonds. The catalyst works by adsorbing both the ethylene and hydrogen onto its surface, where the reaction is facilitated. Hydrogenation has wide-ranging applications in the chemical industry. It is used to produce a variety of saturated hydrocarbons, which are fundamental in the manufacture of fuels, plastics, and other synthetic materials. The reaction provides an excellent example of catalysis in action, demonstrating how catalysts lower the activation energy and allow the reaction to proceed under milder conditions. Educational demonstrations of hydrogenation often involve the conversion of vegetable oils to margarine, illustrating the transformation of unsaturated fats into saturated fats, a process that has significant nutritional and industrial implications. Safety is an important aspect, as hydrogen gas is flammable, and the reaction must be conducted in controlled environments with proper precautions. Ultimately, the hydrogenation reaction between ethylene and hydrogen is a cornerstone of industrial chemistry. It elegantly illustrates the principles of catalysis, bond transformation, and the production of everyday materials from fundamental chemical reactions. The reaction between acetone and bromine, alpha bromination. Acetone, a simple ketone, reacts with bromine in an acidic solution to undergo alpha bromination. In this reaction, bromine adds to the carbon atom adjacent to the carbonyl group in acetone. The process involves the formation of an enol intermediate, which then reacts with bromine to substitute a hydrogen atom with a bromine atom. The reaction proceeds with a noticeable color change. Bromine, which is brownish-red in solution, becomes decolorized as it reacts with acetone, providing a clear visual indicator that the reaction is complete. Alpha bromination of acetone is an important reaction in organic synthesis. The resulting alpha-brominated ketone is a valuable intermediate for further chemical transformations, including nucleophilic substitution reactions and the synthesis of complex organic molecules. The reaction highlights key concepts in organic chemistry, such as enolization, electrophilic substitution, and the role of acid catalysis in facilitating chemical transformations. In laboratory demonstrations, the rapid disappearance of bromine's color is a dramatic way to illustrate reaction kinetics and the power of chemical reactivity. Safety considerations include handling bromine with care, as it is highly corrosive and toxic. Protective equipment and proper ventilation are necessary to safely conduct the reaction. In summary, the alpha bromination of acetone using bromine is a classic organic reaction that offers both visual appeal and deep insight into fundamental chemical processes, making it a favorite demonstration in both research and education. The reaction between phenol and formaldehyde, phenol-formaldehyde resin formation. When phenol reacts with formaldehyde in the presence of an acid or base catalyst, a condensation polymerization occurs that forms a phenol-formaldehyde resin. Phenol and formaldehyde combine to create a network polymer through a series of electrophilic aromatic substitution reactions, resulting in a durable thermosetting plastic known as bakelite. The reaction begins with the formation of a hydroxymethyl derivative of phenol, which then undergoes further condensation reactions to form methylene bridges linking the aromatic rings. This creates an extensive cross-linked structure that is both rigid and heat-resistant. The exothermic nature of the reaction is harnessed industrially to produce plastics that are used in a variety of applications, from electrical insulators to cookware handles, thanks to their high thermal and chemical stability. In laboratory demonstrations, the transformation from liquid reactants to a solid resin is visually striking as the mixture gradually thickens and solidifies. This provides an engaging example of polymerization, a fundamental concept in materials science and chemistry. The phenol-formaldehyde reaction has historical significance as one of the first synthetic polymers, marking the beginning of the plastics industry. Safety is important during this process, as both phenol and formaldehyde are hazardous chemicals that require careful handling. Proper protective equipment and controlled conditions are essential during synthesis. Ultimately, the formation of phenol-formaldehyde resin illustrates the power of condensation reactions in producing durable, useful materials from relatively simple organic compounds, embodying the essence of industrial chemistry and polymer science. The reaction between ethylene glycol and oxalic acid, esterification to form diesters. When ethylene glycol reacts with oxalic acid under acid-catalyzed conditions, an esterification reaction occurs that forms diesters known as oxalate esters. In this reaction, the hydroxyl groups of ethylene glycol combine with the carboxyl groups of oxalic acid, releasing water and forming ester bonds. The process is reversible and requires careful control of conditions to drive the reaction toward ester formation. This reaction is an excellent example of condensation reactions in organic chemistry. As water is removed from the reaction mixture, the equilibrium shifts to favor the formation of the diester product, a principle that is widely applicable in synthetic organic chemistry. The resulting diester has unique physical and chemical properties that make it useful as a solvent and as an intermediate in the synthesis of more complex organic compounds. The reaction also illustrates the importance of acid catalysis in speeding up the esterification process. Sulfuric acid or another strong acid is often used to catalyze the reaction, allowing the reactants to combine more efficiently. In laboratory settings, the progress of the reaction is often monitored by observing changes in physical properties such as viscosity and refractive index, as well as through spectroscopic methods. Safety considerations include handling the acids and organic solvents with care, ensuring that proper protective equipment is used to avoid skin and eye contact. Ultimately, the esterification reaction between ethylene glycol and oxalic acid is a clear demonstration of how simple organic molecules can combine to form more complex and useful compounds, highlighting the elegance of condensation reactions in organic synthesis. The reaction between acetylene and hydrogen, synthesis of vinyl acetylene. Acetylene, a highly reactive alkyne, can react with hydrogen under controlled conditions to form vinyl acetylene, an important intermediate in organic synthesis. This reaction involves the partial hydrogenation of acetylene, where one of the triple bonds is reduced to a double bond, resulting in the formation of vinyl acetylene. The reaction requires careful control of temperature and pressure to ensure that the hydrogenation stops at the desired stage. The process is catalyzed by a metal catalyst, such as palladium or nickel, which facilitates the transfer of hydrogen atoms to the acetylene molecule. This selective hydrogenation is a fine example of how catalysts can direct the outcome of chemical reactions. Vinyl acetylene is a valuable building block in organic chemistry, used in the synthesis of polymers and other complex molecules. Its reactivity allows it to participate in a variety of further chemical transformations. The reaction illustrates key principles of catalytic hydrogenation, including the role of catalysts in lowering activation energy and controlling reaction selectivity. In industrial settings, this reaction is optimized for maximum yield and minimal side reactions, showcasing the importance of process engineering in chemical manufacturing. Safety is a concern due to the flammability of both acetylene and hydrogen. Reactions must be conducted in controlled environments with appropriate safeguards to prevent accidental ignition or explosions. Ultimately, the synthesis of vinyl acetylene from acetylene and hydrogen is a powerful demonstration of selective hydrogenation and catalysis, providing valuable insights into both fundamental organic chemistry and industrial applications. The reaction between sodium and ethanol. When sodium metal is introduced to ethanol, a fascinating reaction occurs that produces sodium ethoxide and hydrogen gas. In this reaction, sodium reacts with the hydroxyl group of ethanol, liberating hydrogen gas and forming sodium ethoxide, a strong base used in various organic reactions. The reaction is milder than sodium's reaction with water, yet it is still exothermic and vigorous under the right conditions. The process demonstrates the reactivity of sodium with protic solvents. While water reacts violently with sodium, ethanol's lower acidity leads to a more controlled reaction, although hydrogen gas is still evolved. Sodium ethoxide is an important reagent in organic synthesis, often used in elimination and condensation reactions. Its formation highlights the versatility of alcohols in participating in deprotonation reactions with active metals. The visual cues of the reaction include the effervescence of hydrogen gas and the gradual dissolution of sodium metal as it forms sodium ethoxide. The reaction provides an accessible introduction to the concepts of acid-base chemistry and redox processes. Safety is essential when handling sodium and ethanol, as both chemicals are flammable, and the reaction produces hydrogen gas, which is highly flammable. Proper ventilation and protective gear are required during the experiment. Historically, the reaction between sodium and ethanol has been used as a model for understanding the behavior of alkali metals in organic solvents. It provides foundational insights into how metals interact with organic compounds. In summary, The reaction between sodium and ethanol is a gentle yet instructive demonstration of metal reactivity, base formation, and gas evolution, making it a valuable subject for both educational purposes and industrial applications. The reaction between benzene and chlorine, catalyzed by iron 3 chloride. Benzene, a simple aromatic hydrocarbon, undergoes a substitution reaction with chlorine in the presence of a catalyst such as iron 3 chloride. In this reaction, chlorine replaces one of the hydrogen atoms on the benzene ring to form chlorobenzene. The reaction is an example of electrophilic aromatic substitution, a fundamental process in organic chemistry that preserves the aromaticity of the benzene ring. The mechanism involves the formation of a complex between chlorine and the iron of Phe chloride catalyst, which generates a highly reactive electrophile. This electrophile then attacks the electron-rich benzene ring, leading to the substitution of a hydrogen atom by chlorine. The reaction is exothermic and proceeds smoothly under mild conditions, which makes it a staple in synthetic organic chemistry for preparing chlorinated aromatic compounds. Chlorobenzene, the product, is a key intermediate in the production of a wide range of chemicals, including pesticides, dyes, and pharmaceuticals. Its synthesis from benzene and chlorine is both efficient and industrially significant. Visual demonstrations of this reaction often emphasize the change in properties from the original benzene to the chlorinated product, and the process illustrates how catalysts can significantly alter the course of chemical reactions. Safety considerations are important because benzene is a known carcinogen and chlorine is highly toxic. Proper laboratory procedures and protective equipment are necessary when handling these chemicals. In conclusion, the reaction between benzene and chlorine catalyzed by iron 3 chloride offers a profound insight into electrophilic aromatic substitution. It highlights the interplay of catalysts, reactivity, and molecular structure in organic synthesis, serving as an essential example in both academic and industrial chemistry. The reaction between nitrogen dioxide and water, formation of nitric acid. When nitrogen dioxide, a reddish-brown gas, dissolves in water, it undergoes a reaction that leads to the formation of nitric acid and nitrous acid. This process begins as nitrogen dioxide reacts with water molecules to produce a mixture of acids. The reaction is significant in atmospheric chemistry because it is one of the key processes that lead to acid rain. The overall reaction is complex and involves multiple steps, but the net result is the production of nitric acid, a strong acid that can have harmful environmental effects if deposited from the atmosphere. In urban and industrial areas, the reaction between nitrogen dioxide and water is a major contributor to environmental pollution. The formation of acid rain can damage crops, corrode buildings, and impact aquatic ecosystems. The chemistry behind the reaction is a fine example of how gas-phase pollutants can dissolve in water and transform into corrosive acids, highlighting the interplay between air and water chemistry. Visual demonstrations of this reaction in a controlled laboratory setting help students understand the environmental consequences of industrial emissions and the formation of acid rain. Safety is paramount when handling nitrogen dioxide and concentrated acids. Proper ventilation and protective gear are necessary to prevent exposure to toxic fumes. Ultimately, the reaction between nitrogen dioxide and water is not only a fascinating chemical process, but also a sobering reminder of the environmental challenges posed by industrial pollution and the need for sustainable practices. The reaction between potassium, iodide, and lead-1 nitrate. When solutions of potassium iodide and lead nitrate are mixed, a double displacement reaction occurs, resulting in the formation of lead iodide. Lead Iodide is an insoluble yellow solid that precipitates out of solution, creating a striking visual contrast with the original clear solutions. The reaction is driven by the low solubility of lead-2 iodide in water, which causes it to form as a solid. The other product of the reaction is potassium nitrate, which remains dissolved in the solution. This reaction is an important demonstration of the precipitation process in aqueous solutions and is commonly used in analytical chemistry to identify the presence of lead ions. The vibrant yellow color of lead-2 iodide serves as an unmistakable indicator of the reaction's progress and provides a clear visual cue for students studying chemical reactions. The process also reinforces the principles of ion exchange and solubility rules, showing how certain combinations of ions will lead to the formation of insoluble compounds. Safety is important when handling lead compounds, as they are toxic and require proper disposal and protective measures. In summary, the reaction between potassium iodide and lead nitrate is a classic precipitation reaction that illustrates key concepts in aqueous chemistry, offering both visual appeal and scientific depth. The reaction between ethylene and bromine, electrophilic addition. Ethylene, a simple alkene, reacts with bromine in a classic electrophilic addition reaction to form 1,2-dibromethane. In this reaction, the bromine molecule is polarizable and, in the presence of the electron-rich double bond in ethylene, becomes activated. This leads to the formation of a cyclic bromonium ion intermediate. Subsequently, a bromide ion attacks the intermediate, opening the ring and resulting in the addition of bromine atoms to the formerly double-bonded carbons. The reaction is typically carried out in an inert solvent, and the product, 1,2-dibromoethane, is a colorless liquid. Its formation is accompanied by a decolorization of the bromine solution as the reddish-brown color of bromine disappears. This reaction serves as a fundamental example of electrophilic addition, a reaction mechanism that is central to organic synthesis. It illustrates how the reactivity of alkenes can be exploited to form more complex molecules. Educational demonstrations of this reaction often highlight the color change as a dramatic indicator of the chemical transformation, engaging students and reinforcing key concepts in organic chemistry. Safety measures include proper handling of bromine, which is corrosive and toxic. Adequate ventilation and protective equipment are necessary for the safe execution of this reaction. In conclusion, the addition of bromine to ethylene is a prototypical organic reaction that not only demonstrates the power of electrophilic addition but also provides a visually engaging and educational experience in organic synthesis. The reaction between carbon dioxide and water, formation of carbonic acid. When carbon dioxide dissolves in water, a reversible reaction occurs that forms carbonic acid. This process begins as carbon dioxide gas is absorbed by water, where it reacts with water molecules to produce a small amount of carbonic acid. Although the reaction is relatively weak and reversible, it plays a significant role in natural systems, including the regulation of pH in oceans and the formation of acid rain. In the atmosphere, carbonic acid is in equilibrium with carbon dioxide and water, and this balance influences environmental processes such as weathering of rocks and the buffering capacity of natural waters. The formation of carbonic acid also serves as an important example of acid-base equilibrium in aqueous solutions, highlighting how weak acids can form and dissociate. In controlled laboratory experiments, the reaction is demonstrated to show how changes in carbon dioxide concentration can affect the pH of water. While carbonic acid is not as strong as many industrial acids, its formation is crucial to many biological and environmental processes. Overall, the reaction between carbon dioxide and water, resulting in carbonic acid, underscores the delicate balance of natural chemical processes that sustain life and shape the environment, making it an essential topic in both chemistry and environmental science. The reaction between benzene and nitric acid, nitration of benzene. Benzene, a fundamental aromatic hydrocarbon, reacts with nitric acid in the presence of a catalyst, such as sulfuric acid, to undergo nitration. In this electrophilic aromatic substitution reaction, benzene is transformed into nitrobenzene as a nitro group replaces one of the hydrogen atoms on the benzene ring. The mechanism involves the formation of the nitronium ion, a powerful electrophile generated from nitric acid and sulfuric acid. This ion attacks the electron-rich benzene ring to form a sigma complex, which then loses a proton to restore aromaticity. The reaction is exothermic, and the formation of nitrobenzene is marked by a change in the physical and chemical properties of the original benzene, creating a compound that is more reactive in subsequent chemical transformations. Nitrobenzene is an important industrial chemical used in the manufacture of aniline, dyes, and other aromatic compounds, illustrating the practical applications of nitration reactions in chemical synthesis. The process demonstrates key concepts in organic chemistry, including electrophilic aromatic substitution and the role of catalysts in generating reactive intermediates. Safety is critical during nitration reactions due to the corrosive nature of the acids involved and the potential for runaway reactions. In conclusion, the nitration of benzene is a classic organic reaction that provides deep insight into the behavior of aromatic compounds under electrophilic attack, serving as both a foundational laboratory experiment and a cornerstone of industrial organic synthesis. The reaction between sodium and chlorine, formation of sodium chloride. When sodium, a highly reactive alkali metal, meets chlorine gas, an explosive reaction ensues, producing sodium chloride. Sodium loses an electron to become a sodium ion, while chlorine gains that electron to form chloride ions. These oppositely charged ions attract each other to form sodium chloride, a stable ionic compound commonly known as table salt. The reaction is highly exothermic, releasing a burst of energy that is often accompanied by a bright flash and intense heat. The dramatic nature of the reaction highlights the power of redox processes and electron transfer between elements. Sodium chloride is not only essential in everyday life as salt, but also plays a vital role in numerous industrial processes, ranging from chemical manufacturing to food preservation. This reaction serves as a vivid example of how highly reactive elements can combine to form compounds that are stable and useful. It illustrates fundamental principles of ionic bonding and electrochemical reactions, which are central to inorganic chemistry. In educational demonstrations, the reaction is often performed on a small scale to safely capture the visual spectacle and to explain the underlying chemical principles. Safety measures are paramount due to the explosive nature of sodium and the toxic properties of chlorine gas, necessitating controlled conditions and appropriate protective equipment. Ultimately, the reaction between sodium and chlorine is a cornerstone of chemical education and industry, encapsulating the transformation of raw elements into a compound that has shaped human civilization. The reaction between aluminum and oxygen, formation of aluminum oxide. When aluminum is exposed to oxygen in the air, it undergoes a slow yet important oxidation reaction to form aluminum oxide. This process begins as aluminum atoms lose electrons to atmospheric oxygen, resulting in the formation of a thin, protective layer of aluminum oxide on the metal surface. The oxide layer is notable for its durability and its ability to prevent further corrosion of the underlying aluminum, a phenomenon known as passivation. Despite aluminum being a highly reactive metal in theory, The rapid formation of this oxide layer makes it appear resistant to corrosion, a property that is exploited in many industrial applications. The reaction is central to the production of aluminum in the metallurgical industry, where controlling the oxidation process is essential for producing high-quality, corrosion-resistant aluminum products. The formation of aluminum oxide also serves as a key example of redox chemistry and surface phenomena in materials science. Safety concerns in this reaction are minimal under normal conditions, though industrial processes require precise control to avoid unwanted oxidation during processing. In summary, the oxidation of aluminum to form aluminum oxide is a fundamental chemical reaction that underpins the metal's widespread use, highlighting the interplay between reactivity and protective surface chemistry. The reaction between hydrogen sulfide and metal ions, formation of metal sulfides. Hydrogen sulfide, a gas known for its characteristic rotten egg smell, reacts with various metal ions to form insoluble metal sulfides. When hydrogen sulfide is introduced into a solution containing metal ions, the sulfide ions combine with the metal ions to form solid metal sulfide precipitates. This reaction is often used in analytical chemistry to test for the presence of certain metal ions, as the precipitates have distinctive colors. For example, lead sulfide forms as a dark precipitate, while copper sulfide may appear as a black solid. The reaction not only provides a clear visual cue, but also illustrates the concept of solubility rules and selective precipitation in solution. In industrial contexts, the formation of metal sulfides is significant in processes such as ore processing and wastewater treatment, where unwanted metal ions are removed from solution as solid sulfides. The reaction is driven by the low solubility of metal sulfides in water, which forces the equilibrium toward the formation of the solid precipitate. Safety is important when handling hydrogen sulfide, as it is highly toxic and poses serious health hazards even at low concentrations. Proper ventilation and protective equipment are mandatory. Overall, the reaction between hydrogen sulfide and metal ions is a classic example of precipitation chemistry, combining visual appeal with practical applications in both environmental and industrial chemistry. The reaction between acetic anhydride and water, hydrolysis. Acetic anhydride, a common acetylating agent in organic chemistry, reacts readily with water to form acetic acid. When acetic anhydride is introduced into water, it undergoes hydrolysis, a reaction where water molecules break the anhydride bonds, leading to the formation of two molecules of acetic acid. This reaction is exothermic, releasing heat as the chemical bonds are broken and new bonds are formed. The process is straightforward yet highly useful in organic synthesis and industrial processes. Acetic acid, the product of the reaction, is an important chemical used in the production of vinegar, plastics, and numerous other industrial chemicals. Its formation via hydrolysis illustrates how anhydrides are converted into acids in aqueous environments. The reaction also serves as an important demonstration of nucleophilic attack, where water acts as the nucleophile that breaks the acetic anhydride bonds. In laboratory demonstrations, the hydrolysis of acetic anhydride is used to illustrate reaction kinetics and the influence of temperature and concentration on reaction rates. Safety considerations include careful handling of acetic anhydride, which is a corrosive substance, and the exothermic nature of the reaction, which requires controlled conditions. Ultimately, the hydrolysis of acetic anhydride to form acetic acid is a key reaction in both academic and industrial settings, offering a clear example of chemical transformations and the principles of nucleophilic attack and acid formation. The reaction between calcium carbonate and hydrochloric acid. Calcium carbonate, commonly found in limestone, reacts with hydrochloric acid to produce calcium chloride, water, and carbon dioxide. This reaction is a classic acid-carbonate reaction, where the acid reacts with the carbonate ion to release carbon dioxide gas. The formation of carbon dioxide is accompanied by fizzing and bubbling, which are clear indicators of the reaction taking place. As the reaction proceeds, the solid calcium carbonate gradually dissolves, transforming into a solution of calcium chloride. The release of carbon dioxide gas is visually dramatic and provides a tangible example of a gas evolution reaction. This reaction is widely used in educational demonstrations to illustrate acid-base reactions, as well as in various industrial processes where limestone is used to neutralize acidic conditions. The process is exothermic, though the heat released is moderate, and it highlights the importance of acid-base chemistry in both natural and industrial settings. Environmental considerations are also relevant, as this reaction plays a role in natural processes such as the buffering capacity of oceans and the formation of geological features. Safety is generally straightforward, though appropriate handling of hydrochloric acid is essential to prevent burns and other hazards. In summary, the reaction between calcium carbonate and hydrochloric acid is a foundational chemical process that demonstrates acid-base interactions, gas evolution, and the transformation of solids into soluble compounds, providing an accessible yet instructive example of everyday chemistry.